Hiya. So in this video, we're going to look at an example or examples, plural, of inner products for vector spaces. And so in particular, we're going to look at Euclidean vector spaces. So one of the kind of standard ones that we first see is something that we've probably seen when we were younger. And this is what's called the canonical vector space, or the, canonical inner product, or the dot product is probably what you've heard. And so what is this? So this kind of helps us see where this angles and distances and all of this is kind of going to go into. So the dot product that you've probably seen before is you just take your vectors, right? And you multiply each component one at a time and you add them up. So here, if you recall, why is this not wanting to write? There we go. X1, Y1, all the way up to Xn, Yn. Now, fun little exercise. So this is what's known as the canonical inner product or the dot product. And at this point, well, maybe you could save this for a little later if you want. If you feel comfortable, try and see how this is an inner product, right? So there's the three things we have to show. You have to show symmetry, linearity, and positive definiteness. So try to show that this is an inner product. If you're still a little hesitant and you want to see a little more examples, we're going to go over 2 examples next. So hopefully this will kind of set some groundwork for that. But in these cases, we're actually going to give an example in the sense that we're actually going to throw numbers at this game. So example 1.23, 1, 2, 3, very fun and easy. So here we're going to start off with some 2-dimensional vector space V. And we're going to have some basis E1, E2. Notice how I'm writing it with brackets, which means it's not ordered. I know last time I said we're going to talk only about ordered bases, but apparently I lied. Mwahaha. Evil. So how are we going to define an inner product? Well, I'm actually going to give you the definitions or the equalities for some of these things. So I'm going to say E1, E1 is equal to 3. E2, E2 is equal to 5. And E1, E2 is equal to 0. So what is the inner product for any 2 vertices? So for here, what you have to notice is that using symmetry and linearity, we can determine the value of inner product of any 2 vectors. Now, first, I'm telling you that's an inner product. So that's kind of nice. We know it's an inner product, but we want to know explicitly how do we find this as the 2 vectors, right? So here, let's figure it out. So symmetry, what's symmetry again? So symmetry is saying that x, y is equal to y, x. And linearity is saying lambda x mu y z is equal to lambda x z plus mu y z. Okay, so what we're going to do is we're going to start off with some 2 arbitrary vectors. So that we're going to say x is equal to x1 e1 plus x2 e2, because we're told e1, e2 is our basis. And we'll let y equal to y1 e1 plus y2 e2. Okay, so let's figure out the inner product. X, y. We plug in our numbers. So here we have x1 e1 plus x2 e2, y1 e1 y1 e1 plus y2 e2. So first we do linearity in the first condition. I guess I should stop moving this up. So here we have x1 e1 y1 e1 plus y2 e2 plus x2 e2 y1 e1 plus y2 e2. And you're about to not be able to see anymore, so I will have to go up regardless. But now, because of the symmetry condition here, because of this, you can kind of see I can reverse this and get a very similar thing, right? So I can put this part in the back and I would still get a very similar thing. So what this is basically saying is I can do the very similar game with these two components. So what do we get? I get x1, y1, e1, e1 plus x1, y2, e1, e2 plus x2, y1, e2, e1 plus x2, y2, e2, e2. Okay, so what do these equal? Well, we're told e1, e1 is equal to 3. So e1, e1 is equal to 3. We're told e2, e2 is equal to 5. So e2, e2 is equal to 5. We're told e1, e2 is equal to 0. e1, e2 is equal to 0. And by symmetry, e2, e1 is equal to e1, e2, which is equal to 0. So this goes to 0 as well, which basically means I can kind of ignore these middle terms. These cancel, or not cancel, they disappear. And so I'm left with 3x1, y1 plus 5x2, y2. So in other words, if I'm giving any two vectors, this is their inner product. Nice. In the next example, we're going to actually see how do we see if it is an inner product or not. So how do we test this? So here again, we're going to be given some product. We don't know if it's inner or not. We're told the following. So we have e1, e1, and e2, e2 are both equal to 0. And we're going to have e1, e2 is equal to, so here it's blank. So we'll make this equal to 1. I'll have to check my notes and see where this error is, but I'm pretty sure this should be 1. So this is equal to 1. And we're going to see if this is an inner product or not. All right. So what we're going to do is first we're going to see how this works. So by an inner, so we're going to first calculate this. So if I kind of do x, y, if I take two arbitrary points, you can kind of see doing a very similar thing as before, right? So like if we take this whole calculation, but this time we have e1, e1, and e2, e2 is 0, and I have e1, e2 is equal to 1. So what this gives me is x1, y2 plus x2, y1, right? So here, I guess maybe I should just do this first. x1, y1, e1, e1 plus x1, y2, e1, e2, etc. And this whole thing is coming from that one, right? So that's where that came from. So we have x1, y2 plus x2, y2, 1. Okay, so remember there's 3 different things we have to consider, right? We have to think of linearity, symmetry, and stuff like this. So here, I inherently assume that it's linear, right? I just assumed it's linear, and we kind of went with it. We said, okay, if it's linear, then it should hold, right? So if it's linear, we should get this. Now, what do any of the other properties fail? So here we can kind of see that we have this weird thing where they're kind of opposites of one another, right? So here, let me choose a different color. They're opposites of one another. So I'm going to kind of choose a number where things are opposite. So what I'm going to do is I'm going to let x be the vector 1 minus 1. And I'm going to inner product it with itself, right? Now this, by positive definite, so we want greater than or equal to 0, right? By positive definite, this should be greater than or equal to 0. And let's calculate this. So here, this is x1 and y1, right? Because we have it in both places. And this is x2, y2. So here, what do we have? We have x1 is 1 times y2, which is minus 1, plus x2, which is minus 1 times 1. So it's minus 1 plus minus 1 is equal to minus 2. So this makes us sad because it is not positive definite. And so positive definite does not hold. So a lot of times it's positive definite that we end up having issues with, especially when we give kind of these kind of definitions. All right, so we will stop here before next video should be the last video, and we'll be talking about how these kind of help define a geometry of a Euclidean vector space. So I will see you then. Peace.